tell us more about how confinement is work, or how he thinks confinement works.
Right.
2+1 dimensions on a case theories. I just want to say that Parameswaran is a bit under the weather because of allergies, so he might speak in a slightly lower voice. So if you want to come to the front,
Good.
Please don't feel shy about coming to the front.
Right. Okay. Thank you, Sachin. So last time I talked, we went over generalities about confinement, and then I talked about the kind of approach that I was planning to pursue, namely look at the geometry and topology of the space of configurations, gauge invariant configurations, and set up things there and see how far we can push. Okay. So what I want to do today is to take that approach in 2+1 dimensions and see, essentially carry out calculations as much as we can do and see what kind of results we can get. Okay. So I will go over some of the things in some detail. It will be a little technical, but please do stop me and ask questions if there is anything that's not clear. So the general idea is we are going to do an analysis based on the gauge orbit space, okay, which is the space of gauge invariant configurations for the theory. So what are the tools that we need to carry out this analysis? We will need a good parametrization of the fields, which I am going to go over shortly. We will have to compute the volume element on this gauge orbit space, define an inner product and a Hamiltonian, and then do an expansion scheme for solving the Schrodinger equation. The result of all that activity would be an analytic formula for the string tension. And once we have that formula, I will be able to compare that with lattice results and see how good the analysis is. Okay. There is also an analytic formula I can derive for a Casimir energy in the nonabelian theory, for which there exists lattice results as well. So that is another point of comparison that we can do. And then depending on time, I may discuss other proposals for wave functions and so on, string breaking effects, Yang-Mills with Chern-Simons added, supersymmetric theories, entanglement issues and so on. Okay. So that is a general idea, but let me just go over a couple of things. So let us actually talk a little bit about Yang-Mills in 2+1 dimensions. Why is it an interesting thing to study? Well, the one good thing about it is it does have propagating degrees of freedom. If you do 2-dimensional Yang-Mills theory, or 1+1 or 2-dimensional, there are no propagating degrees of freedom. Okay, you can solve the theory exactly on any Riemann surface, but at the end of the day, since there are no propagating degrees of freedom, you are not going to say anything very much that is terribly useful or something that would connect to 4-dimensional physics. Okay. The other good thing about it is that there is a dimension full coupling E square. So no dimensional transmutation is needed. So if you compare to 4 dimensions, we cannot really define the theory in 4 dimensions unless we do the dimensional transmutation, introduce a lambda parameter, lambda QCD so to speak, and define everything in terms of that. Okay. So that is not needed in 2+1, so it is a little easier. Further, the coupling constant is not renormalized, therefore some of the issues of renormalization we simply do not have to worry about, which is nice. And at the end of the day, it might actually give some ideas relevant to 4D physics. Okay. But there is also another interesting context in which this 2+1 Yang-Mills is relevant, which is if you take 4D Yang-Mills or 3+1 Yang-Mills, which is the real physical theory of interest for us, and take the high temperature limit. So you have, if you like, a quark-gluon plasma at high temperatures. Then the theory undergoes a dimensional reduction, as is well known. At very high temperatures, you lose 1 dimension. Therefore, the theory becomes 3-dimensional. So what I am going to say about this 2+1 theory would actually apply to that phase of the real physical 3+1 theory. Okay? And in the 3+1 theory, there is something called the magnetic mass, which talks about the screening of magnetic type interactions in the plasma. And the mass gap we are going to find here is directly related to that. Okay. So it is not just a model theory or a an analysis of just intellectual interest, it may actually also have some relevance to real physics. Okay. Now, let me talk about some of the things we discussed. This is just a recap of what I did last time, just to remind you. So, remember the Yang-Mills action I can write in this fashion, E square minus B square over 2. In the Hamiltonian analysis which I am going to pursue, we took the gauge A not equal to 0. So, E is simply the time derivative of A, and this is of course the magnetic field. Okay. And when you quantize, the electric field is canonically conjugate to A, so I can represent it like so, okay, as a functional derivative. Therefore, the Hamiltonian has this structure. There is a B square term which is obviously, just carry over from here. The E square is a functional derivative operator like so. Okay. So, the E square becomes a Laplace operator on the space of potentials, but the real issue of course is we had to mod out by gauge transmissions. Okay. So, this is the Hamiltonian I am going to deal with. Finally, because we chose A not equal to 0, Gauss law is not a Hamiltonian equation of motion, we had to impose it as a constraint. I went over the Gauss law in some detail last time. The thetas are test functions which vanish at infinity, and with that in mind, this generates gauge transformations of the A which is sitting inside the psi. Okay. So, therefore, imposition of Gauss law means the wave functions are actually gauge invariant. Okay. That is the
Probably a typo in the first line. The B doesn't have an index I. First.
Oh, this one, yes, sorry, yeah, that's right, yeah. Too many dimension changes, I forget. Okay.
Can I ask a question as it is?
Yeah, please.
Reflect my ignorance. So, you took the contribution, we could have also added a Chern sign.
Oh, absolutely, absolutely. So, in fact, that is one of the things, if I get time, I might do that and tell you something about it. Okay. But I am going to just start for the moment with just Yang-Mills and see how far we can go, and then we can talk about Chern-Simons. Okay. Okay, very good. So, Gauss law generates gauge transformations, as I said. Therefore, the constraint tells us wave functions are gauge invariant, and the Hamiltonian then of course reduces from here on the space of potentials to the Laplace operator on the configuration space, which is gauge invariant. Okay. So, the ingredients we need are 3 basically to set up the problem. What are the 3? Oops. I need a measure of integration for this configuration space, which is the integration over all gauge potentials, but modulo gauge transformation, and then we can define an inner product for the wave functions. Okay. So, that is the first step. Second, we need to simplify this Hamiltonian, because remember these involve derivatives of the functional derivatives at the same point, which means in the operator language products of operators at the same point, they need regularization. Okay. So, we had to do that and write down what this looks like. And the third ingredient, once you have these two, is to set up a procedure for solving the Schrodinger equation. So, conceptually what I am doing is elementary quantum mechanics, right. This is what you would do for any problem in quantum mechanics, inner product, Hamiltonian, sit down and solve the Schrodinger equation. Okay. But of course, having said that, we are dealing with an infinite dimensional space. So, therefore, there will be some technicalities involved, and since I am going to start on that, I thought perhaps an inspirational quote might be of some use. So, here we go. Okay. Augustin Frenner said, in choosing a theory, one should pay attention to simplicity in hypotheses only. Simplicity in computation can be of no weight in the balance of probabilities. Nature is not embarrassed by difficulties of analysis. Okay. It is a good thing to keep in mind, because some of the calculations we did when we first did it took almost a year to get the Hamiltonian straightened out. Okay. So, you need a lot of faith to go on. Okay. All right, let us talk about this. Okay. So, we are in 2 dimensions. I can take R2, or I can think of it as a complex plane combining x1 and x2 into complex combination z and z bar. And let us say you are looking at an abelian vector field. Then the 2 components of the vector field can be written like this. There is a di of some function theta, this theta some arbitrary function, and then epsilon ij dj phi. What is this? This is the well known Hodge parametrization. Okay. This is what you know already in classical ENM, which says that you can express things in terms of gradients and curls and so on, right. It is basically the same thing done in 2 dimensions. Okay. But I am going to take this guy and combine A1 plus IA2 as AZ, and of course, there is a conjugate AZ bar, which means this is AZ, which I can write as dz, this is dz operator with this definition of z times theta. Theta is phi plus I theta, the big theta here. Okay. So far it is abelian. The question is, how are we going to generalize it to the non-abelian case? Of course, this is a hard parameterization. So, if you like, you can stop here and say, okay, I am going to then try and impose gauge transformations and so on. But if I use this parameterization by itself, it is not going to help me very much because it becomes very complicated. However, I can think of it in another way. If I am doing SUN gauge theory, theta and phi are SUN matrices. So, theta is a complex matrix, which means I can think of as a parameter for the complex gauge group SLNC. Okay. If I think of it as a parameter for the complex gauge group, I realize this is the lowest order term that I can write down when I do the variation of the group. Therefore, I can use that to kind of integrate up on SLNC to get any configuration and write A in this fashion. Okay, so, M is now an element of the group SLNC. This is of course the conjugate M dagger. M is complex, so M dagger is not M inverse. It's a different matrix. Okay, and this provides then a parameterization of gauge fields that's valid in 2 spatial dimensions. Okay, so that's a good parameterization. And of course, what is M? M lives now in SLNC because that's what I did. So, if I have a group SUN, I go to SLNC. What is that process? I am making every parameter complex. So, that is a complexification of the group. Okay. So, for any group, I can do this for any Lie group, use the complexification of the group. Why is this interesting? It is interesting because if you look at the gauge transformation, which is in homogeneous acting on A like so, there is this extra gradient term. In terms of M, because M already has this derivative, it is trivial to check that M simply undergoes left multiplication by the gauge transformation element. Okay. So, the gauge transformations we have made homogeneous in terms of M, that is a big advantage. Okay. And now notice that of course, G is SUN, M is SLNC. So, G does not get rid of all of, I cannot choose G to cancel M completely. Okay. What that means is that if I take M dagger M, I get something gauge invariant, because the G in the middle cancels out between these two, because for the SUN, G dagger is G inverse. So, I can do that. Okay. So, H matrix here, which is Hermitian, is an element of SLNC mod SUN. That is our basic gauge invariant degree of freedom in 2 plus 1 dimensions. Okay. That is a big advantage. Okay.
How do rotations act, spatial rotations act on that?
Spatial rotations, that is complicated because I made complex transformations. So, what will happen is that it is the derivative which transforms under rotations. M is actually invariant under rotations, it is a scalar. M is scalar, but because A involves the derivative, this derivative transforms in, because it is complex thing, it just picks up a phase from the rotation. Okay. Okay. So, that is the first good news, that we can actually do this. And now I want to ask, how do I construct the volume element? And it is going to turn out to be fairly straightforward. Why? Because all I have to do is to take this parameterization, look at the variation. Okay. Why is that? Because let me just say, if I look at the Yang-Mills action, it starts with a term like this minus various things, and if you compare that to the point particle action, you can see that this is the metric I am starting with on the space. Okay. In fact, I think I wrote it here. If I look at this A dot square term, compare with the point particle action, you see that this is going to tell me what the metric is for this action. So, likewise here the metric is just this. Okay, what is the complication? A is a function. So, this is really an infinite dimensional space, but the metric at the end of the day that you should use for Yang-Mills theory is just this metric. Okay. So that's a good thing. Yeah. Okay. So, what do I do then? I take my expression for A, like this one here, and its conjugate, take the variation, put it here, and so this is what I get. So, okay. So, what happens is that delta A has a D acting on this, delta A bar has a D bar acting on this. I do an integration by parts to put the dd bar together and write it like this. So, that is a metric on the space of fields M that I am interested in. Okay. What do I do with it? Well, it is actually an interesting thing to simplify, because let us look at the two endpoints of this. Ignore the dd bar for a second. I have m dagger minus 1 delta m dagger, delta m m inverse. If I just look at a metric with just those two factors, what is this metric? That is a Cartan killing metric on SLNC. Okay. So, therefore, we can now see how the measure is going to work. I have the Cartan killing metric, but I have this dd bar, and remember, when you go to the measure, you have to take a determinant of the metric. So, the volume measure is a Haar measure on SLNC derived from this Cartan killing metric times the determinant of d bar d. Okay. So, all I have to do now is evaluate this and evaluate this determinant, and then we are home. Okay. So, how do I do that? Well, M is a complex matrix, so I can sure.
Since it is invariant under rotation,
Mm-hmm.
space, so these are, if you wanted to parameterize, it's basically theta, and there's no theta dependence of, is that a way of thinking about it? Because you're reducing, at least at the level of n, you're reducing the dimension, and this gauge symmetry is also giving you a space-time symmetry. This gauge, this gauge field is now giving you a space-time symmetry,
Which is the usual rotation.
so then, okay, so you have only a dependence on radial coordinates or something like that.
No, this could be an arbitrary function. It's a rotational invariant combination, but it can still depend on, because
you said that m itself was rotationally independent.
it's a scalar.
Okay.
It's a scalar function, so it does not transform under,
I see, just as a scalar. Okay.
it's just a scalar function. Okay. Yeah. Okay. So, what do? We take this M, it's a complex matrix. So, you do a polar decomposition just as you do for a complex number, a unitary matrix and a Hermitian matrix rho, right, like this. Then you take SLNC and you say what is the volume? It's a top rank differential form. So, simply write it out, plug this in there, separate into u derivatives and rho derivatives, and just work through this, and it reduces to this. Okay. H is our old friend H, which is M diagram, which is gauge invariant. This is the Haar measure for SUN. So, it is proportional to d mu of H. H is the coset variable, and d mu of u. Okay. Now, you might say, well, I did factorize this, shouldn't I worry about whether I can do the factorization? The good thing is SLNC contains SUN, you can factor out without any topological abstraction, okay, because SLNC mod SUN is a contractible space. So, this is doable. Okay. The d mu of H will be the volume element for the coset, this coset here, SLNC mod SUN. How do I derive it? How do I write it? Well, Cartan tells us how to do that. You start with the Cartan killing metric on the big space, reduce it, you can do that. Okay. So, everything here is pretty much known. I just have to evaluate the determinant of d body. No, rho is buried in H, right, because M dagger M is rho, some kind of rho square will be equal to H, and I am able to write it everything back in terms of H actually. Yeah. Okay. So, let us calculate.
So, what's the left action on
gauge trend.
by an SUN. When your gauge transformation is acted from the left, there is a right action.
There is a right action. You are indeed correct, and that I have to pay a little attention to. I am coming to that a little later. It is an ambiguity in the parametrization, because if you write, if you do a right transformation by an anti-holomorphic matrix, that doesn't show up in A. So the price I pay is an ambiguity in how M is defined. So I have to make sure that everything I do is invariant under that.
So in other words, M and MH, where H is some constant, say for the moment a constant matrix.
Yeah,
You cannot distinguish between the two.
that's right. That's right. Okay, but in the end, it won't matter too much, because I'll ensure that nothing I do is sensitive to that. Okay, that's the idea. Okay, very good. So now let's calculate the determinant. We want to do this, so you do the usual thing, take the log determinant, write it as trace log, and let's look at just the d bar part for a sec. Okay, so what do? I take a variation of this with respect to the gauge field. It's a logarithm, so I get a d bar inverse delta A bar. Okay, and this is a functional trace as well, because this is a functional trace. So this is the expression. Okay, and in ordinary trace, x goes to y, that is evaluating the functional trace, integrate over x. Okay, problem is immediately clear. D bar inverse at x equal to x is going to be singular, as all Green's functions are. So I had to regularize it. Okay, how do I do that? It's a very simple regularization I can use for this purpose. Let's first ignore the fact that there are gauge field dependence here. Just look at the ordinary d bar. Then ordinary d bar on 1 over pi x minus y, these are actually holomorphic variables, even though I write x and y, okay, is just a delta function. Okay. Where does that come from? That's one way to write Cauchy's integral theorem. Okay. So that means the ordinary d bar, g bar for the ordinary d bar is this. That's a Green's function. What happens when I have covariant derivatives? It just factors out like this, because remember, d bar plus a bar so if it acts on something, oh, sorry. Let me write it here. Is this okay?
Yeah.
You can write it like this. Okay. So except for multiplication by m and m dagger inverse, effectively I can use the ordinary d bar Green's function for the theory. Okay. So it turns out that the Green's function for the covariant d bar is just this object with an m dagger inverse here. So when I multiply it by m dagger, that goes away, d bar acts on this, I get a delta function, and then I have x and y become the same because of the delta function, kill it off with m dagger inverse, that works. Okay. And now let's expand this for small values of small differences of x minus y. It starts like this, Taylor expansion here, looks like that. Okay. So if I use this in here, this term doesn't matter because it is 0 color trace when I take the ordinary trace with delta A bar. This is the term that contributes. So delta gamma becomes that, that's finite, and I can put what delta A bar is from the previous page somewhere here, this expression here, do an integration by parts. Here is what it looks like. Okay. Why is this interesting? Because the Weismann-Witten action for m dagger as a Weismann-Witten action for m dagger, let me define it like this. This is the standard definition in 2 dimensions. take a variation on the right of m dagger by some arbitrary theta, it is complex theta here. You can take the look at the first correction, this is what it looks like, which is exactly what we found from this evaluation here. This expression is precisely the variation of the Weismann-Witten theory. So, we conclude gamma is 2 Ca. This comes from the normalization. Ca is the adjoint Casimir operator, quadratic Casimir times the Weismann-Witten theory. Okay? But that is only for d bar. We have to do the same for d, which means I will get a Weismann-Witten for m. Okay? But then I had to put them together, and putting them together, you can add a local counter term to regularize it consistent with gauge invariance. So, the whole log determinant becomes this. Okay. So, I can write that determinant in terms of the Weismann-Witten action for the matrix H, which is a gauge invariant combination, and it works fine. Okay. To show how this combines, you use this Polyakov-Wiegmann type identity. Okay. So, what we have obtained then is really an expression for the volume element that we need. Okay. How do I get it? Let us put it all together now. So, remember the Haar measure on SLNC determinant. The Haar measure separates into two pieces, the SUN Haar measure, the coset space Haar measure, and the determinant we just evaluated. Okay. If you want to now drop the gauge transformations, go to the coset space, you just drop this volume element here, d mu of u, because that is gauge transformation, and here is my integration measure for the configuration space. Okay, manifestly gauge invariant, and it gives you the integration measure. Okay. The problem you mentioned of holomorphic or anti-holomorphic matrices, this is not sensitive to it because Weismann-Witten theory has a Casimir type symmetry, holomorphic transformations and anti-holomorphic transformations on either side, and therefore this is still okay. Okay. It kind of works nicely. Okay. So, step 1 is done. The inner product is psi 1 star psi 2 with this integration measure, that is our result. Okay. And I have just repeated the Weismann-Witten action here. Notice that Ca up in the exponent is really the adjoint Casimir given by structure constants, which means that if you were to do this for the abelian theory, there is no exponential here, and that is exactly the difference that is going to happen for non-abelian versus abelian theory. Okay. Everything in the non-abelian theory has to do with this guy up here. Okay. Is that okay? Okay. So, step 1 is done. Now, we want to go and look at step 2. I was going to say something about the Gribov problem. I mentioned the Gribov problem the other day, that when you factor out from space of gauge potentials modular gauge transformations, you cannot have a global section. Therefore, there is a Gribov problem. Okay. So, why do not I encounter the Gribov problem here? The answer is, you have to ask what is the meaning of Gribov problem here. Okay. A good example to think in that context is, think of S3, this one, right. If I look at this and quotient by S1, I get S2. If I try to use this S1 and say you want gauge symmetry, do the gauge fixing, I have a Gribov problem. But if I quotient it down here, there is no more gauge fixing to be done. However, what is left of the Gribov problem is that I cannot cover this space with just one coordinate patch. I will have to do several coordinate patches, okay, at least 2. So, there is a similar issue that can happen here, that you will have to go from one patch to another. I will not talk more about it, but we know how to do that actually. Okay. When I say patch, I mean in the space of potentials, in the infinite dimensional space. Okay. Now, the second thing is, all the gauge degrees of freedom disappear. Yeah. This is the true configuration space. That is right, exactly. And now I have to simplify the Hamiltonian. Okay. So, how do I do that? Well, here is what I am going to do. Let us look at the Wilson loop operator for a second, and which of course we know is a path ordered exponential like so over some curve. Now, the gauge potentials that I showed you, I can rewrite in terms of H in this fashion. Okay. Notice that I have DH inverse here, m dagger minus 1 m dagger plus this. Here of course is 0, there is nothing here, it is here. What it means is that the potentials I showed you is an m dagger gauge transformation of this data here DH inverse. Okay. So, therefore, because of the gauge invariance of the Wilson line, I can convert this into just DH inverse. Okay. So, every Wilson line can be expressed in terms of the matrix that I showed you, the H. Okay. No surprise, because Wilson line is gauge invariant, that is what you would expect, right. What it means is that Wilson line is also providing us with a complete set of observables for the theory. In fact, if anything, it is an over complete set. Therefore, I should be able to use just this object DH inverse to write my whole theory. Okay. So, I am going to call it a current J. I put a Ca over pi, so that it really looks like the current of the Weismann-Witten theory that I just showed you. In terms of A, it is like so. So, this is the quantity of interest. Okay. So, that means I can convert the Hamiltonian to this variable here, and then I can do various calculations with it. So, let me show you how that works.
So I did have to ask something. There are places where the quotient thing by itself is not free. There are m's for which quotient free. Like case transformations which not fractions or
You are talking of the reducible type, correct? That is right. So,
in our experience with the matrix model, we found that the configuration of space for irreducible connections has some dimension.
yeah,
But for reducible ones, we found that there are additional relationships between those gauge
that's
invariant,
right. That's right.
variables that you have.
Yeah,
Therefore, the configuration space is it suddenly becomes smaller at certain places.
that is right. But I am ignoring all reducible connections here.
Yeah. So what I wanted to ask is, there will be issues of, so they occur as I think in algebraic geometry they are called CZJs.
Mhm.
Really extra relationship,
Right.
polynomial relationships.
Yeah.
between-
Yeah,
So presumably there will be
there will be some configurations.
CGs which will
Yeah,
change the dimension of the configuration.
there will be some configurations for which I had to pay attention to that. That is right.
Usually what happens is that if you thought you had six gauge invariant variables, independent ones,
Mhm.
then they collapse to 4 or 3.
Right, right, right. Yeah, that can
Which
happen.
means that there are relationships.
That is right.
And there are only
Yeah.
3 independent.
Yeah, but what has happened is that I impose this boundary condition on the gauge transformations, right. If I have a space where I require that the gauge transformations go to 1 at infinity, okay, in the Hamiltonian picture, that eliminates all reducible connections.
So you are working with pointed numbers.
Yeah, that's right. Okay, that's what I'm doing. If I were to try and do this in the covariant picture, then I can't do that because there will be some incident like thing where the G cannot be equal to 1 on the top boundary, and then I have the issue that you mentioned. Okay, but in this case it's okay. Okay, so let's talk about how to convert everything into the J language, where J is this current here. And okay, so let's take a derivative of psi with respect to A. So the idea is psi actually depends on J, so I can go by chain rule like so. So I had to calculate this derivative here, and then when I do the kinetic term with two such derivatives, then T acting on psi is this two pieces. One is a second derivative, and the other is the first derivative square term with second derivative here and first derivative here. Okay. So, there is nothing profound there, it is just chain rule for differentiation, that is all we do. And what is the variation of the J? because I need to calculate this object here. You can just work it out from the definition of J, use this relation here, and notice that I have delta M diagram inverse. So, I want to convert this into d bar in this fashion, and if I do that, I will come back to that question. This one. It's DHH inverse. I just put a constant factor. Yeah. Okay. So, this J with the CA over pi is the current of the Weismann-Overton theory that I showed you. So, that is why I thought I will tack on the CA over pi. Okay. Okay. So, we look at the second derivative term here, and then of course, I have to evaluate this as well. This is not too difficult because I have delta J and I have this, and I can take the A derivative here, convert this to A bar by this equation here, so then I can use the A bar derivative also. Okay. So, that is not so bad, but I will come back to this point. But then the second derivative here, when I evaluate, I find this expression here. Okay. Why? Because these are at the same point in the Hamiltonian. So, therefore, when I do this, there is a coincident point limit of the waveform of the Green's function. So, it is exactly similar to what we found for the measure calculation. In fact, it is identical. So, I can use the same technology to calculate it, and I find that it is here. It is proportional to J itself when you finish evaluating this, and M here. Did I not write M? Oh dear. Oh, it is on this. Yeah, it is here. This combination is what I call M. Why is it? Why do I call it? It is the dimensions of mass. This is the basic mass scale of the theory that we are going to have. Okay. So, I evaluate this, I put it into the Hamiltonian, and here is what the action looks like. The term with the two derivatives, remember the coefficient here was a single derivative of J with respect to A, another single derivative of J with respect to A. That is easier to evaluate, you get this expression. Okay. So, what I have done is I did a regularization which I did not tell you about. Remember this ambiguity that Sachin pointed out. Okay. I have to do a regularization of these expressions keeping this in mind. We found a regularization that we could do. You take the ordinary Green's function. So, here is my Green's function that I want to regularize. I multiply by a slightly thickened delta function, but I need some combination of H matrices to make it consistent with that holomorphic or anti-holomorphic transformations that I showed you, and then use this definition. There is a parameter epsilon which is like a short distance cutoff which defines this. Okay. So, it is a bit of work, but we can do it, and once you do that, here is what you find. There is a term with one derivative of J multiplied by J, a term with two derivatives say J with this omega. This order epsilon means there are regularization corrections which are not important later. Okay. But take a look at this, this is interesting. This tells you every power of J is going to give me energy M. Okay. It is a counting of J's here. So, you start seeing how there is a mass gap in the theory. Okay. The second thing is, look at this expression. This is exactly the singular terms in the operator product expansion of two currents in the Weismann-Overton theory. Okay. Why is it appearing here? It just appears, but it is a natural object. So, there must be some deeper way to see that, but I am not sure we know the answer to that. Okay. But that is what comes from the calculation. It is very neat object.
Here U and V are spatial points on the spatial slice, right?
Yeah, but holomorphic combinations. So, you
I understand, but in the Weismann-Overton conformal field theory, Z is X and T.
If you think the right, but this is like a Euclidean version if you like.
Yeah.
Okay. So, remember when you were,
What I meant is that there's no time here.
there is no time, it's a Euclidean version. Okay. So, remember, I mean you do that, right. I mean when you do conformal field theory, the commutators are defined by taking it off real axis and doing some contour integrals. So, there is some continuation that we do. Okay. But there must be some nice deep reason why this is appearing, right.
I guess what I meant to say is that in the corresponding conformal field theory calculation, it's a statement about space-time.
That is correct.
Whereas here your
Right.
observation is that it is only about space.
Only about space.
Unless you want to somehow bring in some boundary.
Right. Yeah. So, I have no time because it is Hamiltonian, it is at equal time, but you are right. Yeah. So, some analytic continuation of the time dependent 1+1 theory to the 2 Euclidean dimensional theory would probably, I mean that is what I should be saying. Yeah. Okay. What about the what about the magnetic fields? F here is a magnetic field Fij if you like, but it has only Z and Z bar components. So, it is Fz Z bar, and you just use this expression for A and A bar, just nothing to be done. As I told you, this is a M dagger transformation of this data here. So, it is trivial to evaluate the field strength. It is going to be D bar on this, and then M daggers come on both sides because F is a covariant object. Okay. So, therefore, magnetic field becomes this, which I can regularize again with some sigma. This is my thickened delta function, and write it like this. So, here we are, we have the Hamiltonian finally, this term, this is a kinetic term, this is a potential energy term which I wrote in terms of M also, and that is it. Okay. So, now we have an expression for the Hamiltonian on the gauge invariant configuration space. Okay. So, that is basically step 2. So, what do we want to do now is, so remember I told you there are 3 things we need to do. One is the integration measure and the inner product, we did that. Expression of the Hamiltonian, regularized and so on, we did that. Now, I need to solve the Schrodinger equation. Okay. So, we need an expansion, but we would like to focus on long wavelength modes because we are interested in the infrared of the theory. The ultraviolet is perturbation theory, we know what to do with it. Okay. But then we have a little bit of an issue here. So, even though I want to look at low energy physics, let us take a look at the one loop effective action. Just standard Feynman diagram perturbation theory for 2+1 Young Mills. I have F mu with F mu, this is the correction. Notice that the correction has 1 over the magnitude of momentum, which I write like so, okay, and E square appears here. So, if you think in terms of perturbation theory, when is this small? This is small if E square, which has dimensions, is smaller than the momentum square root of delta square here. Okay. So, E is not really a coupling constant in the sense that I can do perturbation theory. It is a marker. It tells you modes of higher momenta than E square, treat them perturbatively. Modes of momenta lower than E square, treat them non-perturbatively. That is all it says. It's kind of a marker for you. Okay. It does not really serve as an expansion parameter. Yeah.
So, at one side the perturbation theory will be valid
Correct.
because of lambda is smaller, and the other side it won't be, so we have to resort to non-perturbativity.
Correct. Yeah. I mean what I have done so far in terms of the Hamiltonian, that is general. So, I could even do perturbation theory in the Hamiltonian language with the Hamiltonian I showed you.
So, I will do 10 quantum mechanics perturbation.
Oh, absolutely. Just the usual Rayleigh Schrodinger perturbation theory, you can do that. Okay. So, what I am going to do is, I need an organizing principle. So, we are going to do something slightly unusual. Remember, M is E square Ca over 2 pi. By the way, one more thing to say, Ca is 0 for the abelian theory. So, there is no mass gap for the abelian theory. Okay. That is another thing. So, what we are going to do is to say that we will treat M and E independent parameters. They are not, they are related by this relation, but we are initially going to treat them as independent parameters, set up an expansion scheme, and at the end put M equal to this object here, E square Ca over 2 pi. Okay, that is just to get an organizing principle for the various terms. We also need to scale J in some fashion to do that. Then here is how it looks. The Hamiltonian I split into two pieces. This is the kinetic term that you already saw. This is the magnetic field square term, and this is the cubic term from that omega that you saw before. Here, remember, this omega has two pieces. There is this term and this term. So you treat this perturbatively. Okay. So here is how I am going to split, and so H1 is going to be treated perturbatively. H0 I am going to solve exactly. Okay. Now that is not standard perturbation theory, remember, because there is M here. Okay. And in particular, this term which generates mass for J is a non-perturbative effect. Okay. So it's very different from standard perturbation theory. Okay. That's fine. Once we have this separation in mind, we take the wave function to be of this form, where f is some arbitrary functional of J. Put this in here, solve the Schrodinger equation, and you get a series of recursion relations. Okay. That's what we do. Okay. Of course, what is the Schrodinger equation that we are solving? It's just H psi equal to 0, right? Because we are interested in the vacuum. So I am going to take the Hamiltonian on psi equal to 0. Okay. That is the equation. Okay. So we just get a bunch of recursion rules. Is that okay with everyone? Yeah. Okay. So now what does it look like? The lowest order, this is the recursion relation for the 2J coefficient F2, looks like this. K and K bar are momenta. Solve this, you get this wave function. Okay. So you calculate these parameters here from solving this, find F2 from here. F2 I split off a K square and then write this H is this, put that back, here is my wave function. Okay. So this is the lowest order approximation to the ground state wave function of the Yang-Mills theory. Okay. Very good. Can we do higher? Yes, we have done the higher ones. I won't go over this for now. I will come back to that later. Okay. So we can do first order if you want, but let us pause for a second with this expression we have here and ask, can I now say anything sensible about the theory? I have a wave function now. Okay. This is a ground state wave function. So let us
do a normal ordering somewhere.
there is one normal ordering I did, which is
Why is the ground state energy 0?
it should always be 0. This is a point that you are asked to choose a normal ordering with when the ground state energy is 0. Why? Because this is a point that somehow is not very often emphasized in field theory. The reason is the following. You want to realize Poincare group in a unitary way, and Poincare group contains this commutation rule with the boost and energy going like the Hamiltonian. So let me call it H. Okay. Take a vacuum expectation value of this. If the vacuum is to be boost invariant, this must be 0 and this must be 0. Therefore, expectation value of H must be 0. So if you want to have your theory to preserve Poincare invariance, you must choose a regulator so that there is no 0 point energy. Okay, that is important. In a relativistic field theory, bottom of energy is not your choice; it is given to you by the algebra. That is important thing. Okay. So that is what I do. So I did one normal ordering here in the magnetic field term here. This is precisely done to obtain this result. Okay. Okay, so let us take this and look at what happens to this when I take low momentum. Low momentum means this is negligible compared to m here. Okay. So this becomes m plus m, 2m, and remember d bar j with d bar j is the square of the magnetic field. Therefore, the wave function looks like this object here, f is just minus f square. This is the Yang-Mills f square spatial components, coefficient 1 over 4 g square, where g square is me square, okay, from there. So, this is the simplification of the y function square from the low, for the low momentum modes. Okay. So, all you have to do is, you can think of it now, how do I do calculations, expectation values here? That is now like a 2D Yang-Mills theory, okay, because I only have the Fij, the spatial component. So, I can do the calculation. So, I will not go through this detail, this is just to calculate how to obtain energies and so on, but you just take the Wilson line, calculate, you immediately get an area law. Okay. Now, since I did not go through calculation, let me also say that the computation of Wilson lines in 2D Yang-Mills theory has been done by a number of people. I believe it goes back to Rozakov. There is a calculation by Gross and Washington Taylor. There is a different calculation by Ed Witten many years ago, and so on. So, all the, I can either use their results and read off this one, or I can sit down and calculate, it is the same thing, you get this. Okay. But the important thing for us is that we get an area law with this wave function, that is the area of the curve C, and sigma r is this number here. R is the representation to which the Wilson line belongs. Adjoint Casimir, quadratic Casimir of the representation R divided by 4 pi E4. Very simple formula, okay, at the end of the day. Okay. So, you can now ask, can I compare this with experiments? Well, there are no experiments, we mean lattice simulations. Okay. So, this kind of string tension, sigma is the string tension, in 2 plus 1 dimensions has been calculated by a large number of different lattice groups. Most of it is done by Michael Tepper's group, but then there are these follow up work on that. Cases and Narayanan has one, Haridas and Manjumdar have an SU2 calculation, these guys in Jena, they have done G2, a number of people. Okay. And I want to show you the results, here it is. Okay. This is from Michael Tepper's group. K is going to pick the representation for you. So, fundamental representation, antisymmetric, rank 2 antisymmetric representation, rank 3 antisymmetric, and so on. So, the lower numbers here in red are the lattice values. The upper numbers come from this formula that I just showed you here, this formula here. And you can see that it is very close agreement. Okay. If you look at the deviation, this is probably the worst of it, it is about little over 2%. Okay. Everything else is much closer, and the large and limit is almost on top of each other. Okay.
The lattice numbers appear to be lower than the black numbers consistently.
That is right, that is right. So, I did not talk about the corrections to our formula. I am going to do that. The first set of corrections we calculated move us closer to the lattice. Okay. But of course, we are talking fractions of a percent, right, which is and then I should say that this is not the only data. There have been a lot of other work, about 25 different groups and representations have been tried, and they all seem to work. Okay. Now, so when you take a group like G2, which is the one analyzed by Andreas Wipp and collaborators, then there are so called screenable representations, which I mentioned last time. So, the value for G2, if you look at the Wilson line, it goes like that. Okay. So, it is this slope I am talking about when I say compare with G2 value. Okay. The string breaking, which is what causes this, is something we will talk about a little later. Okay. There is one other issue that came up.
That gives you a new scale in the theory.
That is right. So, we can try to predict where that breaks. So, we try to do that. We do not get it as accurate as 2% or anything, but we still get something reasonable. Actually, we can predict that actually. Okay. So, there is one other issue. The result that I showed you involves Casimir, quadratic Casimir operators, and then if you look at the ratios of string tensions to fundamental, arbitrary representation to fundamental, and do a large N expansion, it has this structure. Oh, by the way, I forgot to say, I did not use large N, but all the results we find are consistent with large N expectations. Okay. So that rather works out. But the key point here is that there are 1 over n terms here, whereas there is another law that people are fond of writing, which arises from in super Young-Mills theory analyzed by Douglas and Schenker, is something called MQCD analyzed by Hanani, Strasser and Zaffaroni. There is some, this is not entirely sharp, but there is some work by Herzog and Klabiner which suggests maybe this is what you should expect. And then a general argument was given by Harmony and Schiffman that this is what you expect. Okay. Why? They said if you do 1 over n counting in just Feynman diagram perturbation theory, only even powers of n come. So, how can I get odd powers in this formula? Okay. But it turned, and on the other hand, there is a very strong lattice evidence for Casimir scaling that this formula is correct from all this lattice work. So, what is going on? I think the issue was resolved by these people, Greenside, Lucini and Taylor. They realized that Harmony and Schiffman missed a piece in their argument, which is that if you try to compute the energy of something like so, you expand in powers of various contributions, various exponentials. This is the time t. You are going to pick the lowest one, and that is what is going to give us something. Okay. It is possible to have at finite t cancellations between different terms in this expansion to give 1 over n square, but if you first take t going to infinity limit, you are going to pick the first term and you can have 1 over n in it. Okay. And they actually give examples of how this can be done, this can arise. Okay. So, therefore, the point we are trying to say is large t and 1 over expansion, 1 over n expansion, they are not commutative. Okay. So, therefore, one has to be careful. Okay. Very good. Now, let us talk a little bit about the corrections. So, we calculated one set of corrections to the string tension. I will not show you that result, it's quite a hairy calculation.
The point that you made, would that also extend to finite temperature calculations, non-commutativity between
Yes, I think so. Yeah.
finite temperature?
Yes. So, one has to be careful in simply naively taking the large N counting from Feynman diagrams and saying, oh, here is what I expect. No, you have to be careful. Okay.
Because I know that people do it lightly all the time.
That is right. The time t I am talking about is like the beta.
That's why I said, that's why I asked about
So, it is indeed an issue. I mean, I do not know specific contexts, you may know where this is important, but definitely that is something to pay attention to. Okay, let us talk about the corrections. So, we calculated the corrections. So, here is the uncorrected formula, and here are the corrections. There is some issue with some integrals we could not estimate, we had to bound it. So, that is why these corrections are like so. Okay. Notice that that is a very, very small correction, okay, 2%, maybe 2.5% something compared to this one. Okay.
So these corrections are coming from what?
Remember the recursion relation I showed, the quadratic term I solved for. Now, there is a cubic term, the next term is the cubic term. Remember this recursion relation I established, this one. So, I calculated F2 in this what I showed you so far, but there is an F3 and you can ask what is the implication of that. So, the full y function has the quadratic term and a cubic term and of course, higher terms as well. So, we took this cubic term and calculated all the possible corrections. Okay. Maybe I should go further up, maybe I do not know, but there is only so much one can do. This is a quite a hairy calculation because it involved summing up 8 infinite series of terms which are organized by powers of m over m plus k square. Okay. So, it took a while to get the answer for that. Okay. But the good thing is, notice that it is moving in the right direction as far as the lattice result is concerned, and nevertheless it is a very small amount. So, it does not vitiate what we found already. Okay. So, there are of course higher corrections we have been calculated. Okay.
further corrections
My expectation is they would be, but I have no where is.
Some of the lattice numbers were, I mean, maybe they themselves have error bars.
They also have some small error bars, yeah. But what we found is something very interesting, which is that these 8 series, if you start summing up, the first series gives you a large correction. The second series sums up and almost completely cancels it. The third series gives you something. The fourth almost cancels it. So, there is some kind of funny thing going on. So, we are doing a poor man's way of organizing the terms. There must be a better way to organize where it becomes obvious, right? But we haven't found that actually. Okay. I have, can I take 5 minutes more maybe? Yeah. I will say one more thing about it, which is that let us go back to the inner product for a second and look at this exponential factor here. So, one thing that you could do is to take this factor, absorb it into the definition of the wave function, so that the integration measured looks like that after you redefine your wave function. Okay. Is it very clever thing to do? Maybe, maybe not. But what it means is that the Hamiltonian also picks up these factors from here. Now, if I take my H field, which is the Hermitian matrix that I showed you, and expand for small in a small region around the identity, simplify this H prime Hamiltonian, I can calculate that, and here is what I find. Okay. The first term, there is a second derivative term, there is this term and higher terms. This I think everyone would recognize, it looks like a massive scalar field. Okay. So, therefore, there is a kind of a scalar field in the theory. This is the perturbative gluon. Okay. This is what you would do in perturbation theory, namely go here and calculate. But you also see that this is not quite perturbation theory, because if you were to calculate the propagator in this theory, because it is like a massive scalar field, it's going to involve the Fourier transform of that. Okay. But M involves a coupling constant. So, you do not see this in perturbation theory. But if you expand in powers of M square, that is like perturbation theory, but that is an infinite series. So, already at this stage, this is equivalent to summing an infinite series of terms in perturbation theory. That is the important thing. Okay. Now, the good thing is that if I have a scalar field, then let us calculate the Casimir energy. So, there is some, you can argue that there is some intermediate regime where this kind of representation is useful. It is not strictly perturbation theory, but it is not full infrared limit. But in this intermediate regime, can we calculate anything with this? Well, one thing we can do is to do Casimir energy between 2 parallel plates. Okay. People have done that simulation on the lattice, so we have something to compare with. Okay. So,
Do you recognize it as similar as something like one of the well-known approximations like iconal, or where you sum up a class of ladder diagrams?
there is a, that is right, there is a particular series of diagrams. They are not ladder diagrams, but there is a particular series of diagrams. Yeah, that is right. Yeah. You can sort of make a connection. Yes. Yeah. In fact, long before this, I did a perturbation theory resummation of terms to get the mass gap, and I found 1.2 times this mass. Okay. So, it is very close coming from both sides actually. Okay. So, let us do the Casimir effect. The parallel plate conducting plate boundary condition is this: the tangential electric field must be 0, n is the normal vector to the plates. So, impose this condition, you see that that is equivalent because of this condition to Dirichlet conditions, sorry, Neumann conditions on phi, because it involves a derivative. Okay. So, all we have to do then is to take the scalar field theory with the mass m, we calculate the Casimir energy with Neumann boundary conditions, and you get some formula. Okay. And what is the formula you get? It looks like this. Okay. Everything here is given to you. This is not a fudge parameter at all. This is all given in terms of Casimir constants, I mean quadratic Casimirs. Same here, these are polylogarithms. X is the distance between the two plates. The only parameter we do not have much control over is A. A is actually 1 in our calculation, but we have reason to believe it could be somewhat different. Okay. So, I am going to do the following thing. Let us take the lattice result, which was done by these guys here. Take this one parameter as the only parameter in the problem. These exponentials are given to you rigid, there is nothing you can do, okay, and find the best fit for A. The answer is the two agree dramatically over a whole range of values. Okay. This is the distance for various distances between the two plates to within a percent. However, A comes out to be, I do not know if I wrote it here, the best fit value for A is 0.97. Okay. In our calculation it was 1. So, at best we are off by 3%. Okay. So that is quite nice that we can get this, and I should emphasize the exponentials, because exponentials are important. We are putting exactly the value from our calculation here.
Have you asked the lattice people what is the error bound on their calculation?
Yeah, they have some error bar, but not, it is actually not very bad. In 2 plus 1 you can get much better than, yeah. And so, yeah, so the point is that if we made an error in the mass term that we had, exponential would have a correction, which means it will be dramatically different, because exponential, it magnifies the errors, right. Now, the m that we found, this comes from the m, by the way, is also the propagator mass you would find for the perturbative gluon, which is what this shows you, because this is like the perturbative gluon and this is the mass gap. And therefore, if you do finite temperature 4D Yang mills and look at the high temperature limit, this is the magnetic mass you would find. Okay. So, that means you should, so the formula that I have is m is E square Ca over 2 pi. When you compare with 4 dimensions, this should be related to 4D coupling times the temperature times Ca over 2 pi. That will be the magnetic mass that you would be using in the plasma phase of the theory. Okay. One short argument and I will stop. Now, there is another interesting observation we can make, which is that I showed you that this is like a scalar field. So, let us stay at this level and write down the wave function for the theory. It is a scalar field. So, this is the wave function that everybody knows, right. That is the wave function we get. So, now I say take these phi's and translate back into the variables that I had before, because there was a difference between phi, little phi from h and what I call big phi here. Okay. So, put that back in and here is what you find. Okay. That is your wave function for the theory. And now you can ask the following question. Suppose you allow me to say that the wave function only depends on the current j, then I can say give me a wave function that depends on j, which when I reduce to perturbation theory where j goes like d phi, I get this expression. That is exactly the quadratic term that I showed you. Okay. Why is that important? Because it shows there is a certain robustness to the calculation. Okay. And further, you can also show that this will also indicate that this is consistent with Lorentz invariance of the theory. Okay. So that is important thing. Okay. So, therefore, there is some rigidity, you cannot just change your wave function as you like. Okay. After our work, other people tried to guess other wave functions, there are some discussion of that, but I will not do that today because I have gone over time. So, let me stop here for today, and next time, depending on what I hope to do is I want to come back to the dual superconductivity picture, which is useful in 4D, say a few things about it, and then ask the question whether any of these things can be done in 4D. Okay. I will also comment on string breaking effects and supersymmetric case and the Yang-Mills-Chern-Simons as well. Okay. But let me stop here for today. Okay. Thank you. I'm sorry.